Hello, this is a lecture series for Chemical Engineering Thermodynamics, and right now we are at lecture 4. Just for the recap, the lecture 1 is Introduction to Thermodynamics, lecture 2 is about first law of thermodynamics, then lecture 3, that's about equation of state, which is the relationship between pressure, volume, and temperature. Now we are at lecture 4. It's time to go on to another law of thermodynamics. In a big picture, there are 4 laws on the thermodynamics itself. The very first law is called zero law, first law, second law, and third law, respectively. The first law of thermodynamics, the zero law of thermodynamics is basically what we call the law of thermometer. The first law is the law of energy conservation, and then the second law, which will be explained in this lecture, is called the law of entropy, and the third law is the zero temperature law. In this lecture, lecture 4a, we will discuss the introduction on the law of entropy, which is consistent with the content in the text, the Introduction to Chemical Engineering Thermodynamics by Professor Smith. We are in chapter 5. Let's start with the zero law of thermodynamics. The statement of zero law of thermodynamics is as follows here. If you have object A in thermal equilibrium with object B, and then B is in equilibrium with object C, and therefore C and A are in thermal equilibrium with respect to each other. That's simple enough. Just like mathematical equation, you have x equal to y, x equal to z, therefore y should be the same as z. But in this case, it is physical properties or physical behavior. If you have object A and B in thermal equilibrium with respect to each other, that means A and B share the same temperature. And then if A and C also share the same temperature, that means 3 bodies share the same thing. Okay? It is very simple, very straightforward. But you might ask what's a big deal about this law. It is something like a common sense. We use this zero law almost every day, especially when we try to use thermometer. That's why we call this zero law to be law of thermometers. If you consider a thermometer, which is basically a piece of a glass rod filled with liquid, when you heat it up, the liquid expands. When you cool it down, liquid contracts. Okay? The question would be, if you just fabricated a rod of thermometer, you fill in the liquid, how can we put a mark onto the thermometer itself? Think about that. If I have boiling water and I have a piece of thermometers, unmarked thermometers, right now it's just a plain glass filled with red alcohol. Once you put the thermometers into the boiling waters, then the alcohol should expand to some certain level, and then once they reach equilibrium, the level of alcohol will not change anymore. This is a state that we call thermal equilibrium. Both thermometers and the boiling water are in thermal equilibrium with respect to each other. Therefore, they share the same temperature. So if I put a mark here to that level, and then I put my thermometers to measure the temperature of another object, this purple object. And if the temperature read at this point reach the same level as what I previously observed in boiling water, then I can employ this zero law of thermodynamics to say that right now boiling water and that purple object should share the same temperature as well, and this particular temperature is labeled as 100 degrees Celsius. Okay, because the temperature in degrees Celsius is marked with respect to the behavior of water. we set the 0 to be the freezing point of water, and we set 100 degrees Celsius to be the boiling point of water. In between, we just linearize the temperature. So the temperature change in linear manner between 0 and 100 degrees Celsius. So this is one big application of zero law of thermodynamics. For the first law of thermodynamics, we discussed in detail in lecture 2, both 2a and 2b. In short, normally we said that the energy is conserved. It can be transferred through the system boundaries in only two forms, heat and work. Within the system, the energy can be converted from one form to another, and there are three forms of energy: internal energy, kinetic energy, and potential energy. Okay, so the very first equation that we learned for the first law of thermodynamics is delta U equal to Q plus W. Okay, that can be further derived for closed system and for open system. Just to make things a little bit easier, you can memorize that if you can say that your system is closed system, then you can write this particular equation for first law of thermodynamics. For open system, then you can write this equation. But essentially, these two equations were derived from the same origin. Okay? In closed system, we say that on the left-hand side of the equation is essentially change in energy. Now we focus on the internal energy only. But if you apply the first law of thermodynamics to general problems, you should include kinetic and potential energy as well. Again, the left-hand side is D means change in energy. On the right-hand side, this delta is amount of energy transferred as heat or work. We use differential here to represent small change, and therefore on the right-hand side, the delta in Greek here means that the heat and work transfer is in small amount. So just basically you transfer some amount of energy into the system, making the system having increased amount of energy inside the system. For open system, where we have mass carrying energy together with the mass flow, you have to put energy in three forms: internal energy, kinetic energy, and potential energy together with the mass flow rate here. But if you rearrange the form to put the flow work together with internal energy, then that's the definition of this variable, enthalpy. Okay, we discussed this in lecture 2. And there are two forms of energy transfer in open system. This is energy being carried in and out to the system, and then energy transfer to the system boundaries without the aid of mass flow, which can be into two forms: heat and shaft work. Okay, and the right hand side is the accumulation of energy within the system boundary itself. So all the details in first law of thermodynamics has been discussed in lecture 2. In the first law, main calculation is about finding delta U and delta H. Sometimes we was given delta U, or we were given the condition of initial state and final state so that we can calculate delta U, and then we can use this equation to find out how much heat or work are required to obtain such delta U. But some other times the heat and work were given, the initial state were given, and then we can calculate what should be the final state after the system receives such and such work and heat. Okay? But in order to calculate delta U and delta H, we have to use what we learned in chapter 3 to convert this number or these variables into what we can measure: temperature, volume, and pressure, which is basically the application of equation of state discussed in lecture 3. For the second law of thermodynamics, which is what we call law of entropy, this is what we will learn in this lecture. First, when we discuss the first law discusses the transfer of energy in and out of the system and discuss the conservation of energy. We learned that energy can be transferred through the system boundaries into two forms, heat and work. But the second law does not tell you whether heat and work are different. Okay, in the eye of the first law, energy is conserved and heat and work are essentially equivalent. You can transfer 10 joule out of the system as heat, or you can transfer 10 joule out of system as work. The result would be the same. The system would have 10 joule lower in energy. Okay, so just straightforward for the first law, heat and work are equivalent. They are equivalent in the eye of the first law. However, heat and work in detail, they are not really equivalent. If we look at ourselves as a user, we would prefer work over heat in many circumstances. For instance, we can apply work to the gas system or fluid system so that the system expands, and that expansion can lift the weight that we like. We can lift a car, we can change a tire by just apply some pressure to the fluid, and there's work that we can use right away. On the other hand, heat sometimes can be really hard to use directly. Of course, we can use heat to warm our body, but in the situation if I got a flat tire in my car, we cannot apply heat so that the car lifts up so that I can change my tire, right? So as a user normally, many times, many occasions, we prefer work. So to ourselves, sometimes work is more valuable than heat. We can use work directly, but sometimes we cannot use heat directly. The other way to say that heat and work are not quite equivalent in many ways is to consider conversion from heat and work. Just like these examples, if I have a liquid like water filled in a system, a closed system with constant volume, okay, all the area here is water. I put a shaft and then put a stirrer inside the tank and supply work in form of non-expansion work in this case, because the system boundary has constant volume. Rotating the shaft like this is essentially giving work to the system. And then if, according to the first law, you supplied energy as work to the system, and therefore the system gain energy. If there's no change in kinetic and potential energy significantly inside the system, therefore internal energy must be increased by the work given to the system like this. Increase in internal energy should make the temperature of the system increase, because temperature is an indicator for internal energy. Okay? Once liquid here has higher temperature than the temperature of the surrounding, then there's a driving force for heat transfer from the system into the surrounding, like so. So if you look at this picture as a whole, it seems like we have some kind of instrument that can convert work into heat. Okay? And the harder the work that you give to the system, the higher the heat that you will receive. On the other hand, if I try to reverse, I have the system filled with water with a shaft of stirrer inside the system. If I give heat to the system, can I make the shaft rotate like this? can we get the shaft work back? And you will learn from your experience that no, you cannot. When you supply heat to the system, then water inside should rise, the temperature should rise, and then that's it. Internal energy of the system would increase with amount of energy given by heat, but it cannot release energy into work by rotating the shaft like this. So from this picture, we can say that we cannot fully or spontaneously convert heat into work. So that means on one hand you can convert work to heat, but on the other hand you cannot convert or fully convert heat back to work. So that means heat and work right now they're not equivalent. They're not really the same or they're not as valuable as what we expect from the first law. Just for the obvious examples, if you have money, you can spend money buying junk or buying trash. But once you obtain the junk or trash, you cannot trade that junk back to money again. So that means even though the value that you obtain are the same, but there's a direction involved. You can trade money into junk, but you cannot trade the junk back to money. What does it mean? Money is more valuable than the junk itself. So these two parameters are not equivalent all the ways. Just like heat and work, we can convert work into heat, but sometimes we cannot convert heat back to work completely or spontaneously. So in this sense, work is more valuable than heat. Another example, if I have a pendulum hang from the ceiling like this, and the temperature of the room is 30 degrees Celsius. If I would like this pendulum to move, can I say that I would like to pick some energy from the surrounding and transfer this energy into the pendulum so that the pendulum can move like this? Is it possible? Is this the thing that occurs naturally? You answer right away that no, you cannot do that. Okay? So things like this involve some directions. It means that in one direction it is possible to do that. It has natural tendency to do that. But on the opposite direction, sometimes it cannot do that. Okay? So as I said, work is somewhat more valuable than heat. So in the eye of the second law, then we will start distinguishing between heat and work. And there's a direction involved, as I mentioned earlier. Another example, if you have two blocks of solid, one 15 degrees Celsius, the other one is 25 degrees Celsius. They are connected and the overall system is well insulated. Can I say that let me pick or let me share some energy from the blue part to the pink part so that the pink part has higher energy, higher temperature by the expense of the blue part to get 10 degrees Celsius and 30 degrees Celsius like this? In the eyes of the first law, as long as energy does not dissipate to the surrounding, then the system, the whole system here on the left hand side and the right hand side are the same. The energy are conserved. Okay, so it is okay according to the first law. But you see from your experience that you cannot do that in real life. It is not possible in real life. So there's a direction involved again. The direction from the left to the right does not occur spontaneously, or it does not have natural tendency to occur. On the other hand, if you have 10 degrees Celsius cold body in contact with 30 degrees Celsius hot body, you leave it for a while, you eventually get 15 and 25 degrees Celsius like so. So the reverse direction is spontaneous. Okay, so you can see that one direction is not spontaneous while the opposite direction it is. So sometimes in some situation it really depends on direction. So we are going to use the second law to predict directionality of the process. Okay? There are two kinds of directionality. The first one is called spontaneous change. This is the change where it has natural tendency to occur by itself. Okay? But please be clear that spontaneous change does not mean it has to change. For instance, if I have water in a lake, below the lake there's a dam. If I have a dam and the water above the dam or in the lake near the dam has higher potential energy than waters below. So it has natural tendency to flow from the dam down to the ground level. Okay? But as long as I close the dam, water remains there. It does not flow by itself. So even though the flowing is spontaneous, it has natural tendency to flow downward from high elevation to low elevation. But as long as I have the dam in between, then there's no flow. Okay? So spontaneous change doesn't mean it will change. Okay? It just has natural tendency to change. The opposite thing is called non-spontaneous change. In this case, the process has no natural tendency to change. Just like the dam, I have water in low elevation. The water cannot rise to high elevation by itself. It has no natural tendency to flow that way. But it doesn't mean that non-spontaneous change will never change. Okay? Once again, non-spontaneous change can be forced to change by giving some kind of external energy. Just like water in low elevation has no tendency to move to higher elevation by itself, but we can force it to move by giving it some energy in terms of pump. If we supply pump, we supply energy, then we can carry water from low elevation to higher elevation. Okay? So non-spontaneous change can occur, but with some aids of external energy. So let's start talking in detail about second law of thermodynamics. Unlike the first law of thermodynamics, second law of the second law of thermodynamics has been mentioned in many ways. Okay? For instance, initially, it was stated that time goes in one direction. Certain events are ordered. What does it mean? In general, some people said that the second law is time's arrow. Time goes in only one direction. You cannot reverse time. Okay, so some process goes along the time, but some other process cannot move back in time. Okay, just to make sure that you understand, let's look at this video. We have gymnasts moving up and down. Okay, throughout the video here you will see the movement up and down and up and down, and you see that this video is natural. There's nothing wrong with this video. On the other hand, this video on the right hand side, this athlete going up and down, okay, and up and down again. But this time this video seems weird. It's not natural, and you can tell right away that video on the right hand side is not natural at all. There's some trick to this video. The question is, how do you know that? Even though the movement are the same, you have up and down on both videos, but on the left everything seems natural, on the right it is not. Okay, so it is about time again. When the time goes by, video on the left hand side goes in the direction that is spontaneous. It seems natural. Video on the right, only the first half seems natural, on the right hand on the rest of the right hand side videos does not goes along with the time. Okay, and it was stated that a system left to itself should move according to this situation. First, it will move from more order to more disorder state. What does it mean, order and disorder? You can tell right away which situation is order, which situation is not order or disorder. Okay, a good example is a yard. If you have a yard in front of a kindergarten, you have a bunch of kindergarten kids. Let's say you have 100 kindergarten kids in front of the lawn, in front of the school. Okay, if you put 100 kids, maybe 2 or 3 years old, on the yard in front of the school, obviously all of them would run around. There's no order whatsoever. Okay, if I say that I like 100 kindergarten kids to stay in line, perfectly aligned on the yard in front of schools, that is order state, but it is very, very unlikely to occur by itself. By natural tendency, the chaotic movement or disorder state is more favored, takes place most of the time. Okay, so that means, on the other hand, if you have 100 kids line up in front of the school, perfectly aligned, and you leave that for a while, there's supposed to be a movement, kids are moving around by themselves. Eventually you end up with a random position or random mix of kindergarten kids in the yard. So the system with order state has natural tendency to move into a disorder state. Okay, that's what people have said. People also have said that a system would move from a state of lower probability to higher probability. It seems like it is very obvious that things with higher probability should occur more often. Okay, on the other hand, things with lower probability should rarely occur. So whenever you have something with lower probability and you leave that situation for a while, it should change or proceed toward the state of higher probability. Examples like this: if you have bromine gas, which is orange in color, and you put air on top like so, before we take the separator out, the system is in order, or it has lower probability to occur. But once you remove these separators, bromine would diffuse into the air up there. In molecular level, you see the movement of bromine gas forward or upward into the air, and there's a movement of air downward to bromine. There's a mixing between two gases. So in molecular level, this particular picture seems to have less order, more disorder. Okay, if you look into the term of probability, to get the mixing randomly mixed like this state has higher probability than the initial state where the the orange molecules and white molecules are separated. Okay, so mixing seems to be spontaneous because mixing starts from low probability state and end up with the state with higher probability. On the other hand, if you have mixed gas like in this picture, and then you would like to separate them to get bromine at the bottom and all the air on top, then the state of separation like this has lower probability, and therefore the process does not occur naturally. The process, in this case the separation process, would be considered as non-spontaneous change. Okay. Also, another people said that if you leave the system by itself, it would move from a state of more precious or useful energy to the state of less precious energy. What does it mean? Just imagine you have a hot piece of metals. A piece of metals heated up to maybe 600 degrees Celsius, a red hot metals. You can use that energy condensed inside that piece of metals to heat up anything. You can put underneath a frying pan to make your breakfast, okay? But if you put that piece of metal, red hot metals, in water, like in this picture, energy within the metals would dissipate into water, okay? Now, the dissipation state like this has less energy, not less energy, less precious energy. The total energy remains the same according to the first law, but now energy are dissipated within the system. This system has the state of energy which is less precious. You cannot put this water, let's say if you put the red hot piece of iron inside this water warms up to maybe 60-70 degrees, but you cannot use that energy to make your breakfast anymore, okay? So it is harder to use dissipated energy in this state, okay? So it was stated that if you have precious level or precious state of energy and you leave that state for a while by itself, it will turn into less precious state. Just like in global warming, we have rise in temperature of the environment. The rising of energy or the rising of temperature occurs spontaneously, but we cannot try to condense energy in our atmosphere to use that energy to heat some things up, because now the energy is already dissipated. It is in the less precious state of energy, okay? So in the second law, it was stated there are several things, couple things are stated in second law. First is about direction, okay? It's about direction, the direction which is spontaneous and the direction which is non-spontaneous. The other thing is to distinguish between heat and work. But in the calculation, in the second law calculation, most of the time the calculation should involve the new parameters called entropy. Okay, we will discuss the definition of entropy in more detail in the next lecture. This lecture is just an introduction. Okay, so it was stated that entropy was invented. So somehow this is a new parameters that people has invented. It was invented or introduced in the attempt to distinguish work from heat. Okay, in such introduction, the calculation was done on the engine and one engine, and this engine, this particular engine, was designed to be operated in cycles. We will discuss about the detail of this engine together with the calculation, so that we get the definition of entropy in the next lecture, in the second part of this lecture 4a. Okay, but in a sense it was derived so that the dissipated heat can be calculated and distinguished from the work obtained by an engine. In that case, or during that time, entropy was not given physical meanings. It was just a number or a parameters that can be used, but it does not have a physical meanings at all. Later on, during a couple decades ago, people moved on from thermodynamics and trying to study deeper and deeper in molecular level. Okay, and that comes to what we call statistical mechanics. In statistical mechanics, it considers interaction between molecules and try to correlate that interaction with respect to parameters like what we observe in thermodynamics. We can correlate atomic motion, atomic vibration to internal energy, and therefore people try to somehow make correlation between atomic motion, atomic vibration with respect to entropy as well, so that entropy now will have some kind of physical meanings. Okay, and it was stated that entropy is an indicator for chaotic dispersal of energy and matter, and I would like to emphasize on this word, indicator. You have to understand that entropy is not dispersal of energy or matter. It is just an indicator to state which system has higher chaotic dispersal of energy and matter than the others. Just imagine things like this, just to make things a little bit easier to understand. Temperature is an indicator of internal energy. When you have high temperature, you can tell that that particular system has higher internal energy than the system with low temperature. But temperature by itself is not energy. Okay? So in the same manner, entropy is not the chaotic dispersal of energy and matter, but it is an indicator to tell just which system has higher chaotic behavior than the others. Just like in this picture, if you have colors, balls with different colors, red, green, blue, and yellow, you put them onto the on the floor. It is very unlikely to get the picture on the left hand side. The picture on the left hand side has higher order or lower probability. The picture on the right hand side, on the other hand, has higher probability but lower order, okay, or more disorder. Okay, so if I ask which one is more chaotic, the answer would be the right hand side. Which one has higher probability to occur? Once again, the right hand side. And therefore, if entropy is an indicator for chaotic dispersal of matter in this case, it means that the right hand side picture has higher entropy. Okay, so again, this is just an indicator to tell that this particular system has higher chaotic movement or chaotic dispersal of energy or mass. So if we combine the concept that we previously mentioned, that the system spontaneously move from order state to disorder state, or move from state with low probability to state where probability is high. When you tie this sentence to this sentence, it means that the system normally spontaneously evolve toward the state with increased entropy. Okay, so this sentence said that spontaneous change occur from disorder state to order state, and this sentence said disorder state should have higher entropy. So therefore, when you combine these two sentences together, you get this sentence: the system changes spontaneously to the state where the entropy would be increased. Okay, until the system will reach equilibrium. Once it reaches thermodynamics equilibrium, there will be no longer change in the system. Okay, so one thing is that when we consider the change in any system, whether it is spontaneous or non-spontaneous change here, we are looking at the change before the system has reached the thermodynamics equilibrium. Okay, but once the system has reached equilibrium, there will be no more change unless you disturb the system. Just like you have water at low elevation and water at high elevation, in between you have a dam. Without disturbing a dam, then water would stay separated The high elevation will stay in the lake, the low elevation will stay under. Unless you open the gate of your dam, then the water starts flowing, and that direction can be determined based on the direction of increased entropy. Okay? Once the water in the dam is depleted, then, or if the level of the dam is reduced until the level would be the same as the level of water under the dam, then there's no more flow. The system reaches equilibrium again. But for the consideration of change in thermodynamics, we have to consider entropy change for both system and surrounding. Okay? We cannot consider system only as what we did in first law anymore. If you recall, in first law, the delta U that we consider is a delta U of the system only. We just consider change through system boundaries and then reflect that to be the change in internal energy of whatever inside the system. We never consider internal energy of the surrounding in the first law. But for the second law, in order to predict the change, whether it is spontaneous or not, we have to consider the change in entropy for both system and surrounding. Okay, so this is just an introduction for the second law of thermodynamics. So in brief, we are discussing two things. First, in the second law, heat and work are not equivalent anymore. Okay? The second thing that second law will tell you is about direction of the change of process. There are two kinds of directions: spontaneous change and non-spontaneous change. Once again, spontaneous change has natural tendency to occur, but it doesn't mean that it will occur. On the other hand, non-spontaneous change will not have natural tendency to occur, but again, it doesn't mean that we cannot make it occur. We can make it to occur if we supply some additional energy. Okay, so this is it for the introduction for the second law. Next video we will start deriving or give you an introduction or definition of entropy, so that you can tie the physical meanings of second law to the calculation with the second law. So thank you for watching. See you on the next clip.